Just to introduce myself, in case people don't know me. So I'm Philippa Timmins. I'm head of sales here at Aurochs. I got a PhD in inorganic chemistry from the University of York, which is where I met Peter O'Toole from the previous session. And I've worked for various companies, various instrumentation companies in microfluidics, microscopy, imaging, optics, spectroscopy. So I've had quite a varied career, and I've been with Aurochs for the last 3 years. Britta, Lee, can you just let people know to refresh their browser if they have problems with audio, just to help them out a little bit? And I'll try and speak up. So this is a little refresh of some of the slides from yesterday. I apologise if I'm repeating for people who were here in the session yesterday, but for people that weren't here yesterday, it's just a very brief history of our company. So a lot of people have not heard of Aurochs before, and so it's a good thing maybe to show us a bit of the history. So we heard from Tony Wilson yesterday about the history of confocal microscopy, and he's one of the founders of the company. And so Aurochs was founded in 2004 as a spin out of the University of Oxford engineering department. They first came up with a structured illumination method for sectioning images, and developed the OptiGrid technology on which the Zeiss Apotome is based, and some of you may have heard of that. And all this time we've been working as an OEM manufacturer, so we manufactured instruments for other companies to sell. So we started off with Zeiss. We developed the Zeiss Vivatome. We then went on to work with Andor to develop the Andor Revolution DSD range. So some of you may have heard of the Vivatome or the DSD. We also work with Zeiss on their materials analysis product called the SmartProof 5. And we also work with 3D Histech for their confocal slide scanner. So as you can see, all the way through our history until about 3 years ago, we were manufacturing instruments to go into other people's products or for other people to sell. So in 2017, I joined the company, and so did Lee, who's been on this meeting as well. And we started to sell our products directly to the end user. We really wanted to be in touch with people that were using our instruments, so we could better improve our product range. So we redesigned our confocal instrument, and we launched the Clarity laser-free confocal, and then the Clarity HS, and then very recently the Unity confocal that's sitting behind me here. So all of our products are laser-free. Why do we want to do laser-free? Obviously, many of the confocal products that you come across in your daily work will have lasers, be they laser scanning confocals or spinning disc confocals. We wanted to produce a confocal system that was cheaper, easier to use, and much more reliable. Lasers tend to have some downtime. They might need expensive maintenance contracts, and so they're very expensive to run. We wanted something that was very cheap to run and easy to use. And also a bit safer, so there's no laser safety worries with our instruments at all. We also find with a lot of samples that we get lower photo bleaching and lower phototoxicity when you don't use a laser for your illumination. So we just wanted to save you time and money and make confocal microscopy more accessible to general researchers. So how do we achieve this? People that were in Tony Wilson's talk last night, and if you weren't, we will make it available for you to see later. We'll have seen that they could use a candle to do sectioning. They could use a candle for a confocal microscope. So there's two main differences. Traditional spinning disc systems, so all our technology are spinning disc confocal microscopes. Traditional spinning disc systems that use lasers, they use this traditional Nipkoff spinning disc design based on pinholes. Now you find when you have a pinhole system, this is rejecting a lot of your light. So Rimas and Tony and Mark and others they measured this light throughput in 1996 and found that you lose 99% of your excitation illumination before you even start. Now they have got a little bit better, these systems now, so you can get about 7% light throughput, but you still throw away a lot of your light, which means you need a laser to illuminate your sample. Now in our technology, we have a patented structured illumination disc. So instead of pinholes, we have almost a letterbox shaped aperture for the light to go through. So it's a grid pattern on this spinning disc. And the pattern is 50% dark, 50% light, 50% dark around the disc. So we get 50% of the light throughput to excite our samples. And this just means we don't need the bright intensity of a laser. You could, in theory, use a laser if you wanted to, but you just don't need to. So we usually use an LED light or a metal halide lamp, something like that. So inside our clarity system, I'm going to explain to you in a little while, there's this spinning disc. So this is what the disc looks like. There are 3 sectors on there. So if I turn the whiteboard on and just change colour to something you can see, that there's 3 patterns. Sorry, my circles are a little bit off. So the pattern at the top is a fine pattern. This will give you the highest confocal sectioning, but also the lowest light throughput. Then we have a medium sectioning, medium light throughput, and a coarse sectioning, high light throughput. This is very, very similar to opening and closing the pinhole on a traditional confocal microscope. So you can think of it in a similar way to that. Let me just clear the whiteboard and get rid of it. So how do we achieve laser-free confocal? Again, I apologise if this is a bit of repetition from yesterday, but for new delegates that haven't seen this, then I think it's important to know. So we have a white light source. This can be an LED lamp or a metal halide lamp, whatever you have in your lab, a candle if you wish. So we have the excitation light passes through our spinning disc, and this projects a grid pattern into the focal plane of your sample. Then your fluorophores get excited and they emit light. This emitted light, some of it can pass back through the gaps in the disc, back through the pattern of the disc. And what we do is we take this light path and we project it onto 1/2 of a scientific CMOS detector. Then the back of our disc is reflective. It's got a reflective coating on there. So the rest of the light that can't pass through the disc bounces off the back of the disc. And we take this light and project it onto the right-hand side of the detector. So just to explain what's going on, the light that's gone through the disc, this contains our confocal signal that we want, but it also contains about 50% of the out of focus light as well. The reflected light that comes off the back of the disc, that contains the rest of our out of focus light. So we have one image with confocal and blur, and we have another image which is just blur. So what we do then, we do a simple registration of these 2 images together and we subtract one from the other. And that gives us our confocal image. So this is all done on the fly. You don't have to worry about it. It's all taken care of in our software, but just to explain what's going on. And if anyone needs to go through this again, I'm very happy to explain it offline, or we can organise a demonstration for you. So this talk is all about the Clarity laser-free confocal. You saw Unity yesterday, and you'll see it a little bit later, hopefully, if we have time. But Clarity laser-free confocal is a small add-on that you can add to any wide field microscope. It just fits onto the camera port of your microscope, and it will convert that microscope into a spinning disc confocal system. So it's fast, it's very simple, it's very easy to use, and it's compatible with a very wide range of detectors, light sources, and microscopes, which our support team and R&D team are always moaning about because it makes our support burden quite high. We have lots and lots of configurations that we can use with this confocal microscope. Because it's small and easy to use, it's quite affordable. It has very low running costs as well. So just to highlight the flexibility of this system, Clarity will fit almost any microscope. So we go back about 2 or 3 generations to the sort of Nikon TIE, the Leica DM and DMI 6000, and the Zeiss AxioVert ranges. So we're very, very flexible with what we can do. So these are just 3 examples. So on the left, we have a system on a Nikon microscope, an inverted microscope. In the middle, we have the system attached onto a macroscope from Leica. And on the right, it's one of my favorite pictures. This is a really interesting demonstration that I took part in, where they have a Zeiss microscope, which is actually orientated by 90 degrees, affixed to the wall. And this is for people to look at plant root development. So the roots of the sample can grow downwards while they're being imaged. And as you can see, the Clarity system is very small and compact. So it makes it very easy to add on to these systems. And just another few examples. So the system on the left is at the University of Bristol in Paul Verkada's lab. We were doing some testing on the cryo-clem system there. The second image in is Alex Corbet's remote focusing system, and he's just recently published some results from that, which is really exciting. The third image is on a DM6 from Leica. As you can see, we have different cameras attached to this each time. So we have the PCO Edge, we have the Hamamatsu Ultra Flash, we have the Andor Xyla. And the one on the right is from a lab in Germany, in Mainz. They're doing electrophysiology with the system. So as you can see, it's really, really flexible. I mentioned that it's really easy to use. So we have our own software package called Visionary. Now, when we do demos, people are always commenting about how simple and easy this software is to use. So it's just, if I turn the whiteboard on again and change color. Color red. So this area here is just a big viewer window for your sample, so you can see a live image of your sample. And then down here is like a flow chart of operations. So we can do your XY tile scans, your Z stacks, change color, choose the resolution of your sampling. You can do your time lapse and everything, all in a really simple to use software package. And this is just drilling down, so you can see the different stages that you can go through. There is an expert mode as well for some more advanced stuff. And just to say that our system is also supported in Micromanager. Some people are working in Metamorph. So you don't have to use our software if you don't want to, but if you want the ease of use, then it's probably the best thing. So I just want to finish off with just a couple of examples. So this is a really nice example. We were doing some marketing work actually at the University of Oxford, and they kindly lent us some C. elegans samples. And when we used Clarity to image their samples, they were really excited. So just to show you, the top image here was taken with the Clarity laser-free confocal. There are some differences between the data sets, but hopefully you'll get the main point. This was at 40x, one channel, and it took 14 seconds to do 22 slices. With their, albeit quite old, SP5 from Leica, slightly different objective, and 2 channels, but it took them 10 minutes to take essentially the same image with the same resolution. So they were really, really excited about that result. And just to show the flexibility of the samples that you can use, you can go all the way up to immersion lenses, and you can get down to subcellular levels and look at cell biology, drug delivery, nanoparticles, things like this. Or you could go up to the larger specimens. So it's very, very useful for developmental biology. And this is when you really see the advantages of the speed with these large samples, where you need to screen and get through a lot of samples quickly. So for example, the testimonial on the left from the Tamanka lab at the Max Planck Institute, they did a massive screen of these Drosophila egg chambers, and they really loved that it was done on a DSD2, from Andor, but it's still our technology, which is almost exactly the same as the Clarity laser-free confocal. And this is a fantastic image that was from the University of Helsinki, from Jaakko Mattila. So this is just to show, again, the speed of the system. So they've been using the system for quite a while in their core facility, and they were kind enough to let us see this image of a Drosophila midgut. So they did 4-channel images, 50 different tiles with 4 slices per stack. And they did it in 8 minutes, which is really, really fast for this size of data set. So if Miko is online later, he can maybe tell you how they got this image, because he is the agent looking after the University of Helsinki. I know that the Helsinki guys are not online today. So just in summary, and then we can move on. And I hope that Remus is answering a few questions in the background, so maybe we don't need to answer too many questions afterwards, and we can move on. So Clarity is our unique spinning disk design, but it's based on a long history of structured illumination and sectioning techniques going back many years, all the way through to Tony and Remus's early careers. You get higher light throughput than a traditional spinning disk confocal microscope, and it's faster than a traditional laser scanning confocal microscope. So you get some really good advantages there. It's a really simple add-on to any of your microscopes. We can usually get most combinations working, different light sources, different cameras, things like that. It's safe, there's no laser safety worries. It's much more affordable than a traditional laser-based confocal. So thank you very much for your attention. And perhaps Lee could pick out any questions that Remus has not had a chance to answer while I get ready for the next speaker. So there's just one at the top, just to confirm again from Bojul Chang. Just to confirm again, the Clarity is basically the same as Unity, just one is an add-on and one is an all-in-one microscope. That's a really important point. Yeah, they're based on exactly the same technology. There are some subtle differences. So Clarity obviously fits on your normal microscope, so you have the advantage of your objective turret. So you can use all your existing objectives from your microscope, and it ends up a much more affordable way to get a spinning disk confocal. So if you already have a microscope and, say, a camera, then it's a very affordable way to upgrade that microscope. Unity has one objective inside, so not quite as flexible, but much faster imaging. It's much more automated. And it's more designed for really rapidly getting your confocal images very quickly. Also, Clarity has 3 different patterns on its spinning disk. Unity has 1 single pattern. So they're the main differences, but essentially, yeah, they're exactly the same technology, the same method of getting confocal instruments. So I think Remus has probably answered all the other questions. So I'd like to wrap up there. If there are any more questions at the end of this session, I'll be more than happy to answer them. So now I'd like to ask Nick to join us. Thank you, Nick, for your patience. Hello. Hi. So yeah, Nick is an Oxford Nottingham Biomedical Imaging CBT DPhil student. His doctoral research focuses on optical aberration correction of SIM systems using adaptive optics. He's going to talk to us about microscope AO tools, a generalized implementation of adaptive optics using deformable mirrors. So over to you, Nick.
Great. Thank you very much for the introduction, Philippa, and thank you to Aurochs for putting on this conference for us. It's been really good. Yeah, as I say, I'm Nick, and I'm here to present a microscope AO tools. I mean, any of us who have encountered any form of imaging, which is, I'm assuming, basically everybody here, is well familiar with optical aberrations and the havoc that they wreak on our samples and how they destroy our image quality. The good news is that there is technology that exists called adaptive optics, which is specifically designed to correct for these optical aberrations that appear. So the reasons that these phase distortions destroy your sample quality is because they basically mess up the wavefront, and by having these adaptive optic elements in the beam path, you can flatten out your wavefront again and recover the focus of your light, which is good. That's what we all want. So why don't we just all implement adaptive optics? There's a bit of a process to designing an adaptive optics system. So you think about designing it. If you decide you don't want adaptive optics for some reason, then obviously you don't build one. And then you need to think about the type of imaging that you're doing and what you can reasonably implement in your beam path, price, etc. Put it in your beam path, and then there's a whole process of setting the adaptive optic element up and getting it ready to be used. So these we kind of divide into these 4 stages. So this first one, actually deciding which kind of adaptive optics you should use, is not Microscope AO Tools won't help you there, but the Department of Engineering has a useful resource for helping you make that decision. And equally, Microscope AO Tools won't help you with aligning your system, your AO element into your beam path, but we've developed this neat tool called Beam Delta that will help you to do that. What Beam Delta will help you, not Beam Delta, what Microscope AO Tools will help you with is these sections 3 and 4, which are basically your setup and your use case methods. The only requirement that Microscope AO Tools has is that it assumes that you have an adaptive optic element that is a deformable mirror and that is compatible with a separate software package that we've developed called Python Microscope, which is just a way of implementing control over all your hardware elements that if you've heard any of us from Micron talk at other conferences, you may well have heard us talk about before. So there are a number of key elements in setting up and getting your adaptive optic element, in this case a deformed mirror, ready to be used. The first one is you need to calibrate it. So you need to kind of meaningfully be able to set up your deformed mirror so that you can recreate the aberrations that your system suffers from. And then you need some measure of the success of that. Then you've already you're already looking at the wavefront and you're already seeing your system aberrations, so you should correct those. And then you need to work out, well, do I want to do sensorless adaptive optics, or do I want to just perform direct wavefront sensing? And if you're doing sensorless adaptive optics, you need to come up with a routine and a method that works well for your sample and your imaging modality. So there are a number of methods that we have. This is the first step is calibrating it, because we have a deformed mirror that is a set of individual actuators, and we want to be able to recreate these Zernike modes, which are basically the aberrations that you will be familiar with: coma, defocus, trefoil, astigmatism, spherical aberration. But a deformed mirror is just a silvered membrane. It's usually some kind of thin membrane with a bunch of actuators on the underside of it, and that's not exactly how the aberration modes are defined. So you need some way to map from where your actuator should be moved to into how that recreates an aberration mode on the surface of your deformable mirror. And the way you go about calibrating it is you move each of your actuators through a number of steps. You acquire influence functions, which are just how the actuator influences the shape of your deformable mirror. You arrange those into an influence matrix, and the inverse of that gives you a control matrix, and that moves you from, okay, I have these aberration modes present. Please now apply these voltages to my actuators to recreate, to flatten out my phase wavefront. Acquiring these influence functions, I just put in a single box, but there's actually a number of steps to that. You kind of poke each actuator through a number of steps, and for each step you measure the phase wavefront. So that's the acquire phase image there. You may be wondering how we do that. I will address that question later. And then you measure the Zernike modes that are present, and then you basically fit how the Zernike mode amplitudes change as that actuator moves. That gives you influence functions, and so that's how you go about calibrating your deformed mirror. Having done so, you need some way to evaluate it, and that we call this characterization. Now, ideally, if your deformed mirror is perfectly calibrated, you'll say, okay, please give me one amplitude of defocus, one amplitude of spherical aberration. You get the idea. And that your mirror will give you exactly that shape and nothing else. Now, because of like some mathematical issues, the fact that you're kind of doing pseudo inverses of a large matrix, the fact that there's noise in your system, etc., you never end up with a perfect control matrix. So the actual characterization you end up with is something like this. So you get small amplitudes of other modes creeping in there, and the amplitudes that you have recreated. So the way that we do characterization is we apply one amplitude of each mode. Sorry, I realized that's on my next slide. The way you go about attaining this characterization assay is you apply 0 voltages to all your actuators. So you have in theory, flat mirror that isn't applying anything to it. You acquire an image of your phase that gives you the idea of the background Zernike modes that you have. And then you apply one amplitude of each of your aberration modes in turn, acquire the phase image, subtract out the background Zernike modes. And what you should have is you have your background plus one amplitude of each of your aberration modes. In practice, as you can see here, the graph in the bottom left of the images, you actually get about 0.8, so an 80% reconstruction accuracy for the first 30 odd Zernike modes, and then it starts to drop off. That's just due to you have a finite number of actuators in your deformed mirror. So this is from a 69 actuator deformable mirror, and so you can only recreate you can't recreate some Zernike modes as accurately as others. That's the way it is. But most of the optical aberrations that most of us will be familiar with, things like coma, astigmatism, trefoil, first and second order spherical aberration, focus, those are all encoded by the first 20 or so Zernike modes. So this is a good control matrix, and this will be sufficient to correct for any optical aberrations that you have. So you've calibrated your control matrix. You have this. You've got a characterization assay. It looks something like this. You're thinking to yourself, "Great, that's excellent." So now we go with you want to correct for the system aberrations, and this again is a really simple routine. You measure your background phase wavefront, and then you just apply the opposite shape to your deformable mirror. Again, if you had a perfect calibrated deformed mirror, you would you just need to do that once. But because as you just saw, there's some errors in the you don't get perfect reconstruction of your aberration modes. You do this in an iterative process until you've done either n iterations or your RMS error, so how not flat your wavefront is, gets below a certain threshold. And then you have the best flat wavefront that you have, and you've corrected all your system aberrations. Excellent. But that is now we've got to actually add biology to it, and then it usually gets a bit more complicated because a lot of biology. So in this instance, this is a fruit fly neuron, kindly provided by Josh Titlow. There's no easy way to just get the phase wavefront out of those images. There's no nice point spread functions that you can pull out and go, right, well, these are my optical aberrations. So what you have to do is set up a sensorless adaptive optics technique, where what you do is you apply, say you go, right, I think I probably have some amount of spherical aberration in my system. I'm going to apply different amounts of spherical aberration, measure some quality of my image, and try and maximize that. So if you say you're measuring the contrast between the signal and the noise, you take a couple of images with different levels of spherical aberration, you measure the contrast, and then you can fit your contrast as a value and obtain this A max, which is the kind of the amplitude of that particular Zernike mode that will give you your maximum image quality. Now, there are a few ways you can do this routine, and they basically boil down to when you want to measure your metric, and when you want to apply your corrections. In the left-hand option, you are applying an amplitude of a Zernike mode and measuring the metric immediately, storing that measurement, and then applying the next image. And then once you've got all your measurements for one particular Zernike mode, then you fit, in this case, a Gaussian, find the peak of that, apply that correction, and then move on to your next Zernike mode. In the middle one, the only thing that changes is you're now measuring the metrics once you've acquired all the images for a particular Zernike mode. This has the nice benefit of your images are captured as close together temporally as you can. So if you have a live sample, which is one of the systems that we've been working on, is made for live sample imaging, then that gives you the best measurement of your aberrations without kind of things changing in time. But you still apply the correction after each mode. And in the right-hand workflow, you basically acquire all the images for all the modes, and you only apply one correction at the very end. So you try and correct for all modes simultaneously. This can be useful because, again, you're now shortening the time frame in between your image quality measurements, but it does mean that sometimes your image quality, if you have certain modes that aren't as prominent as others, they can be swamped out by larger aberrations that are present. And if you implement one of these workflows, as we've done, you get something that looks like this, which is a significant improvement in the image quality of, in this case, a neuromuscular junction of a Drosophila. For people who are a bit bored with the flowcharts, this is some actual biology data that we have. So this one was taken through an Aurochs Clarity we attached to an Olympus body, and the samples were very kindly provided by Dahlia from the Yelan Davies lab. And you can see that the adaptive optics makes a significant difference in being able to point out where the DLG is actually localized, and you can actually see some of the structures of the nerve, which is the big magenta structure running through the center. So that's on this system, and then on a different system, which is DeepSim, which is an upright structured illumination microscope. This is more neuromuscular juncture images, again provided by Josh. You can see that the AO makes a significant difference. If you don't have it, then you basically don't see anything unless you significantly boost the levels artificially. But with the AO, there are much clearer structures. So Microscope AO Tools implements a method for calibrating your deformed mirror, doing the characterization, doing the system correction, and it implements the methods you need for any of the three workflows I described. Now, you may be expecting this is the point where I wrap up the talk and ask if there are any questions, but hopefully I've not completely overrun my time, and you'll notice I have a fair bit left to speak. And you may well be aware that there are already a number of proof of principle microscope systems, and so you may AO systems, and you may be wondering why AO Tools is Microscope AO Tools is any different. This is why I prefaced this talk by saying that it was a generalized implementation, because usually, me as somebody who's building an AO system, I build all the kind of software that I need for my imaging modality with my sample type in mind, and with my wavefront sensing technique, and it works on my system. But then any other user who wants to use it has to either recreate all the work that I've just done to make very minor changes, or can't implement my workflow at all and needs to start again from square one. And AO Tools is designed so that you can put it on any system with any deformable mirror using any image modality for any sample type, and you need to make little or no changes because it's well generalized. And I will show you now what I mean by that. So firstly, you notice that I just kept referencing this acquiring a phase image, or acquiring the phase wavefront of your in the calibration, characterization, and wavefront flattening routines. the reason that I kind of made this a bit vague is because usually there are two principal ones that most people use, which is either Shak-Hum moment sensing or interferometric wavefront sensing. And if I have designed my software workflow using interferometry, somebody else who has a Shak-Hum wavefront sensor needs to redo my entire characterization calibration and wavefront flattening routines. But Microscope AO Tools is designed with a suite of wavefront sensing techniques, and either you will download AO Tools, find your wavefront sensing technique there, and just swap over to that by a simple string call in the software, and away you go. Or you go, oh, I'm using some different or new wavefront sensing technique. And then all you need to do is write up the little module that takes. Oh no, sorry, I thought I had something else on the next slide. My bad. That takes a raw image and outputs a phase image. Add it to this suite of metrics, not suite of phase unwrapping techniques, and then you can just swap over to that. But it also means you don't have to re-implement the calibration, characterization, or direct wavefront flattening techniques. And it also means then anybody else who is using the same wavefront sensing technique as you also doesn't have to re-implement any of that either, because they can just swap over to that from the suite of phase acquisition methods. Similarly, you'll see a number of red boxes here to do with measuring this image quality metric. And again, that I kind of kept that a bit vague, because the exact image quality metric that you want is dependent on your sample type and your imaging modality. And so AO Tools implements a suite, again, of image quality metrics that you can pick between. But if you come up with some new metric, or you have one that's better suited to, say, single molecule localization techniques, whereas ours are kind of more for structural illumination stuff, because that's what we've been working on primarily, you can you just implement your metric measurement function that takes in an image of your biology, outputs a number that is your image quality metric, and then put it into the suite of metrics that already exists. And now you don't have to re-implement the sensorless adaptive optics techniques that we've already done the work doing, because again, Microscope AO Tools is well generalized. So you might go, okay, great, but I've actually already got a method for calibrating my deformable mirror. I just want to use the sensorless adaptive optics methods that you've got. And Microscope AO Tools is also good because it allows you to do that. You perform your external calibration routine. You save your control matrix and system correction actuator positions to a file. Microscope AO Tools can read that in, sets them, and then you can just carry on with the sensorless adaptive optics techniques as if Microscope AO Tools had calibrated your deformed mirror. Or say, for example, that you have an offline machine learning correction, like sensorless correction routine, and you go, well, I want to use it for Microscope AO Tools for correcting, for calibrating my mirror, but I want to just then use my sensorless technique because Microscope AO Tools has methods to just be told, please apply these Zernike mode amplitudes to the mirror kind of at random. You can use AO Tools to set up your deformed mirror and then perform your offline sensorless analysis, and then just pass a set of Zernike mode amplitudes to Microscope AO Tools, say, please apply these. It'll do so, and then away you go. Hopefully, what that convinces you all of is that, as opposed to your traditional AO implementations, where a lot of hard scientific work is having to be redone by a bunch of people a bunch of times, with Microscope AO Tools, you can the workload is minimized for people who want to just access adaptive optics. And the nice thing is that the more people who use this and contribute their direct wavefront sensing techniques or image quality metrics, the more universal this software package will get. So yeah, thank you very much to everybody from Micron and the Ilan Davies Lab, and Martin Booth's Dynamic Optics and Photonics group, and Mantis, who's moved away. I will happily answer any questions, and if you would like to download Microscope tools, Python Microscope, which is the hardware control software, and Cockpit, which is the user interface that we've designed, here are some QR codes and some ways you can get through PIP. Thank you very much.
Hi there, thanks Nick, that's really good, we've really enjoyed working with you guys to implement Clarity into Cockpit. It's been a bit of a journey together, but it's really been fun. So there's been a couple of questions popped up from Rito. So the first one is there a rule of thumb how many Zernike modes you can faithfully recreate given a number of actuators? It sounds like one would need 2 to 4 times more actuators than the max number of Zernike modes one can control.
Yeah, so obviously from a mathematical perspective, you've n degrees of freedom, which are your number of actuators, so you should be able to recreate n Zernike modes, but in practice you usually can recreate like n by 2 with any degree of accuracy. So yeah, usually you need about twice the number of actuators for the number of Zernike modes you want to correct.
Okay. And another question from Rito. For the sensorless AO, how messed up can your starting image be? Mild versus wild aberrations. What's the biggest jump in STREL ratio you were able to achieve?
So for the sensors, I don't have a good answer to that in terms of a hard value. I think as long as your image quality metric is sensitive to completely, to even very wild aberrations, and the degree of aberration you have doesn't try and push your deformable mirrors actuators beyond their stroke length, then I would kind of say that the sky's the limit. But it comes down to how well optimized your image quality metric is and what the stroke length on your deformable mirror actuators are.
Okay. And a question from Bob Hartley. Is AO Tools usable in commercial software, or is it on a recursive license like GPL?
I believe it's on a recursive license. So yeah.
Okay. And yeah, as Nick says, you, go ahead and download these tools because they're open source. So have a play with them. Okay, thank you, Nick. If there aren't any more questions popping in, we can move on, but maybe you can stay as a delegate in the background, and if more questions pop up, you can answer them as they come along.
Yep, will do.
All right, thank you very much, Nick. Take care. Okay, so now I'd like Gerard to join the room, if that's possible. Hopefully you're online.
Hello.
Hi there. Good evening. Thank you for rescheduling. Okay, so this is Gerard from Cooled. So Gerard graduated from Glasgow Caledonian University with a BEng in electronic engineering. He helped to conceive and develop the first Cooled products. So he's now been with Cooled for, what, 15 years? And is now their technical director. He's going to talk to us about the benefits of LED in fluorescence microscopy. Go ahead, John.
Thank you, Philippa. I hope everyone can hear me all right. Okay, I'm going to just talk, as Philippa said, about LEDs. I'm going to cover 3 points generally, and that's about LEDs. Actually, about when they first became popular and first came through, and that was around 2016. And it was really about convenience in the early days, about long lifetime and on-off compared to the bulbs that were available back then. Some of those early negatives included poor intensity compared to the bulbs and also limited wavelengths. I'm going to cover some of that and how that's been overcome more recently. And some new positives as well about how LEDs, rather than just being a rather dumb element on the back of a microscope, has now allowed for quite sophisticated control and allowing for better imaging actually, and improving cell viability. So actually adding some value to the images that you can now get from your microscope. Okay, this is an old image about some bulbs and the old mercury bulbs back in the day. Some people might remember these, but they have become a thing of the past. But generally, if you talk about the some of the benefits, the lifetime of standard LEDs, we talk about 10,000, 20,000 hours. In fact, LEDs tend to have their lifetimes quoted at about 100,000 hours, but we have to overdrive them in the systems for fluorescence, really to get that extra bit of brightness out of them, and that's okay as long as you keep them cool. The fact that they don't have any warm or cool down like the bulbs did, which would take about 30 minutes to warm up once you'd switched them on before you could use them, and then when you switched them off, you had to let them cool down for 20 minutes. The fact that you could actually switch an LED on and off almost instantly, talking about microseconds, tens of microseconds here, actually means that the lifetime can actually realistically turns into many years, because if people choose to turn their LED on and off, they only have to have it on when they're looking at a sample or actually taking a picture. And that turns out to be a tiny amount of time compared to the bulbs that had to be left on all day long. So that 20,000 hours is an enormous amount of time. Yeah, so very convenient. Lab managers didn't like the mercury bulbs. The independent intensity control that comes with LEDs as well, because they're fully electronically controlled, allows for things like balancing of different fluorophores on your sample. No need for neutral density filters anymore. If we look at the next slide, here's a typical image again of the old setup, just again showing some of the historical benefits that have brought LEDs into the mainstream. Things like shutters are no longer needed because there's fast electronic switching. Things like the neutral density filters. LEDs now have very precise intensity control, and that can be varied not just across the whole wavelength at once, but with independently per channel. And excitation filters as well, which typically would have to be in an excitation filter wheel, but can now be placed directly into the LED system. So really, it's helped reduce costs, helped reduce a whole bunch of hardware, some of which caused some vibrations itself. Yeah, and actually started enabling much faster imaging than was possible before. So just to very briefly talking on the transmitted light sources here. We've been talking about fluorescence up to now, but transmitted light source is also important. With an LED, you actually achieve a relatively flat and very flat color temperature. No matter, even if you're turning the intensity up and down, the halogen color temperature actually changes. Normally people like to keep it around about a 9-volt setting, which really brings the given a color temperature about 3000. And actually where we can hold the LED. There's another element that's important for LEDs when considering them for transmitted light, and that's the correlated color temperature. And that's achieved by really just balancing the LED and giving it a good green-red region, as we can see here. A typical LED is very cold to the eye and very blue, but some warmer LEDs are becoming much more common. Actually, for transmitted light, there's a lot less UV in a transmitted light LED, unlike the halogens, so it's much easier on the eye. And your eye should dry out less quickly. So LEDs have become pretty mainstream really over the last maybe 5 years or so, even before then. There's been still sort of questions over power and wavelengths, and I'll talk a little bit about that right now. So, do LEDs cover the wavelengths needed? Well, a lot of people, well, they do, frankly. In this image, you can actually see, which has been commonly available for some time now, covering from 365 right up to 740 for Sci-5 and 770. LEDs can go way beyond this, up to 1700 and beyond. actually at the low end, we now have 340 used for Fura 2, and actually there's some other LEDs coming through here down at the deep UV, UVC region, 260, 280, now available, being driven by the sort of needs for sterilization. Not quite sure about the applications for these guys in microscopy just yet, but they are available now. Another region which is important, which there's a lot of concern over, has been the green region with LEDs. As you can see, the curves look a little bit broader here. That's because LEDs are very dim in the green region on their own. So pretty much everyone providing LED sources on the market is using a phosphor in this region. And that's a typical broad sort of spread of a phosphor. There's a few ways of exciting a phosphor. We use a very strong blue LED with a phosphor on top, which is very efficient and strong enough and getting stronger. There's other methods. You may use a laser to excite a phosphor, or a Phillips rod type excitation method. Bit less efficient, but yeah, all good. What you have to remember with all these wavelengths is, like, although the bulbs were quite simple, the bulbs covered the full spectrum. By comparison, actually, an LED doesn't. You need multiple of these LEDs. And actually, in a given system, you may find you only have 4 LEDs or 3 LEDs, or what's becoming quite common is 6, 7, or 8 LEDs. We have a system out there that actually has 16 LEDs, but you only have 4 channels at one time. So the important point here is, if your LED isn't matched to your excitation filter, you'll see nothing. Or if it's poorly matched to your excitation filter, you'll just get a very weak signal. And this is quite commonly the problem with people that feel that LEDs aren't bright enough. So just to go on to talk a bit more about brightness, here's a picture of the traditional metal halide bulb in grey. You can see here. I'll turn that off. With one of our common P300 light source spectrums. So you can see, I mean, powers came on a lot. When I think of when we first launched this product many years ago, it was back in 2006. We were just a tiny fraction of the power of the metal halide, and now you can see how things are growing. And the power tends to be on a trajectory that's maybe doubling every 2 or 3 years. So I think a lot of people are frankly telling us that LED power is enough now. A lot of people, I think Claire Brown's talk yesterday may have brought up the fact that maybe exciting your fluorophores with less power and using a longer integration time is a healthier way of viewing your samples. But yeah, some people still want power, and power is there. How power is quoted is another confusing element, yeah, because although power doesn't really describe what you get at your sample, and we tend to use a phrase irradiance, which really describes power per area, and we'll often quote milliwatts per millimeter squared, and we measure that at the sample, and this result is a comparison taken at the sample. It can be quite misleading for you measuring other places, such as the light guide output. You can actually get the impression you have a lot more power, but that doesn't necessarily make it through to the sample. If you're interested in that, we have a white paper on our website, measuring illumination intensity, which you can have a look at if you want to know more about power measurements. So what else have we got? We've covered some convenience, the long lifetime, the fast on off, and the mercury. And another element is that the LEDs are much greener than the previous bulbs. What we'll bring this on to is that we can talk about performance now. And actually, from the dumb bulb that was in the back of the microscope, LEDs have quite sophisticated control now, and actually can lead to actually improving the image. And when you think about why someone uses a microscope, it's generally to get a picture or a sequence of pictures to create a video. So the LED actually, it turns out, can actually improve that image, improve the signal to noise ratio of that image. It can also help reduce photo bleaching, which means you can image for longer, and improve the cell viability. And these can sound quite incredible from a humble light source, but it actually just comes down to the narrow bandwidth and the high speed of control that you get with LEDs. Here's an image here that shows the reason why improved signal to noise comes through, and that's because, as you can see here, we have the grey is the metal halide again, and in here we have I think it's a 435 nanometer LED for exciting something like CFP, and we can see how well it fits into the excitation passband of the excitation filter here. There's very little of the LED energy actually spilling into the emission passband, and that's important for improving signal to noise and reducing that background. The filters are great. You have really great optical density of 6 blocking on these filters, but they can work. They don't have to work half as hard when you've got an LED there, because there's very little energy to be blocked, and that does reduce the background. Also, there's very little UV. For every photon that creeps through your filters and reaches your sample, and the deep UV is going to be it's going to be causing autofluorescence in background. So just by moving from a broadband light source, even a broadband LED, into using single bands, you can actually have significant improvements in signal to noise. A paper by Sandrine Pross that was out in 2016 showed improvements of up to 7 times actually. So it's quite incredible. In terms of improving cell viability, we have there's a few methods of this. This comes down to high-speed switching. Actually, one of the big improvements is really just about being able to switch the LED on and off very quickly, and actually be able to synchronize that on and off to the exposure time of the camera. And this can be done maybe with a TTL line from the camera exposure to the LED light source. Reducing that needless exposure and that needless illumination on the sample on either side of exposure goes a big way to reducing photo bleaching from when shutters were used or where fast switching isn't used, and it also improves cell viability. A more sophisticated method, which actually I'll refer to another paper by Claire Brown and her group, discussed actually very fast pulses as opposed to a continuous illumination. This is actually maybe a microsecond pulse and then a rest period to allow the fluorophores in the triplet state to come back down to the ground state, and followed by another pulse. And this is, again, has been shown to dramatically improve cell viability and reduce photo bleaching. So just in summary, LEDs have become a very common part of fluorescence microscopy now, and actually are improving the imaging. So I'll end it there, and thank you very much, and thank you for Aurochs for having the show, and thank you for everyone for listening. Any questions?
Brilliant, thank you very much, Jerry. That's a really nice summary of the advantages. I must say, just a comment on your "Are LEDs bright enough?" When I first joined Aurochs and I was going out and doing demonstrations, I always took an LED light source and a metal halide lamp, because sometimes I'd need to switch to the metal halide lamp if something was very weak. But over the last few years, the brightness of the LED lights has just gone up so much, and with a little bit of tweaking of dichroic mirrors and filters, we now don't need a metal halide lamp anymore. The LEDs are definitely bright enough for our use. So yeah, the technology's come on a fantastic way. So you had a couple of questions pop in the background. So Stamatis was, I think you already answered this, but maybe you can reiterate. So he said, yesterday we heard a presentation that TTL switching was faster compared with USB control for certain LEDs. Is this true? Oh, for a certain LED make. Is this true for QLED as well?
I can't comment. Unfortunately, I missed Claire's talk. I will listen to it. But for QLED, no, our slowest TTL speeds for some of our later products are about 150 microseconds. Right now, we're getting under 20 microseconds for our products. And actually, stuff we have been showing recently is down to a microsecond. So TTL is very fast. USB is really limited by the dynamics of the operating system typically.
Yeah, definitely. And Bob Hartley's asking,
Hi, Bob.
260 to 280 nanometers is good for RNA DNA sample purity quantification.
Well, interesting. Thanks for that information, Bob. I believe, yeah, there is some work going on there. I don't understand it. We're doing some work with Strathclyde, looking at 280 and for novel biomedical imaging applications. But what's interesting is the power's really quite strong there now. There are LEDs that go right down to much lower than 260, down to maybe lower into the 200s. But 260, 280 is very strong. So that's a good point, Bob. We'll maybe and there's an application there we'll look into.
Cool. And then a question, is the PE100 white based on the phosphor white LED? This may cause strong background and fluorescence imaging to the point that a shutter in the transillumination path is necessary. Maybe you can comment.
That's absolutely true. It does. That's a weird problem. So it means that a shutter's true, but actually what it also means, another way of getting over that is some people have put a green filter over the transmitted port. But yes, it is a problem. Using a white with a phosphor on it can be problematic when mixed with fluorescence, especially with a blue. It's the blue that will excite the phosphor and cause that background. So okay. Yeah.
Cool. And there's a little bit of discussion between Claire and other people and Ian. So maybe when you go back as a delegate, you can dip in and just read their comments, and not quite questions, they're more comments about the technology. Thank you ever so much for being flexible and rearranging and staying so late. I'll let you go and relax now. And maybe I can call Simon into the room if you're available. Okay, Simon's just connecting. Okay, so just while Simon's connecting, Simon Bush received a Master of Science by Research in Plant Membrane Cytoskeleton Interactions from the University of Durham in 2015, is that right?
Yeah, that's right.
He's been at Prior for a little over 2 years now and is their product manager. So he's going to talk to us about tailored hardware for automated microscopy. And thanks again, Simon, for being so flexible and rearranging everything.
Oh, that's no problem at all. Thanks very much, Philippa. Thanks very much to Aurochs for organising this talk and giving us an opportunity to speak about our products. I was particularly disappointed not to be able to go to FOM in the end, because I was actually born in Japan, haven't been since 1994. But there we are. So I just wanted to use this opportunity to give everybody an update on what Prior are up to these days. So we're established in 1919, and for our first 70 years, we were manufacturers of microscopes, benchtop, student, research microscopes. And then in 1987, we undertook something of a shift into microscope automation as imaging routines started to become more complex and remove the user from some of the more laborious tasks. And we've been very successful in that field for the last 30 years. And we've got quite a wide range of stages and focus systems and things like that that we sold over the years. But last year we celebrated our 100th year in business, which is a tremendous achievement for any company. But now we're looking into the future. So having started in 1919, what's next? What are we doing now in 2020 and beyond? Well, our core business is broadly divided into 4 areas. We manufacture precision components. We've got our own in-house manufacturing. And we use these in the remaining 3 areas, those being microscope automation, nanopositioning solutions, and finally some bespoke microscopy systems, some OEM manufacture products. So I'm going to cover each of those 3 sections and some new products in each area. So first of all, I want to touch on microscope automation, and we've released a new autofocus system, the PureFocus 850. Last year, and this piece of equipment is a hardware autofocus that has quite a lot of versatility and gives the user control over quite a lot of parameters for use in some quite complex experiments. So, like I said, the PureFocus 850 is a hardware autofocus. That means it uses a laser to detect where the sample is in the optical path. So, just on the left-hand side there, I've got a schematic of a reflected light system. So you've got your incident beam coming from your light source. It's then reflected down onto the sample, and then the reflected light from the sample is collected by your camera. Transmitted light obviously comes from underneath the sample, goes through the sample and goes back up to the camera. The PureFocus sits in the same optical path, but slightly offset from it. You have an inbuilt 850 nanometer class 1 laser that's reflected down onto a reflective plane within the sample, and then that signal is reflected back up to a line sensor within the PureFocus head. And the way that these laser autofocus systems work is that depending on where the sample is relative to the objective, you'll get the laser being focused back onto a different area of the sensor. So if the sample's above focus, you'll have the signal focus back onto the left-hand side, for example, and if it's below focus, it's focused on the right-hand side. And in both cases, the signal is quite diffuse; it's spread quite far along the sensor. When the sample's in focus, the signal falls exactly into the middle of your sensor and gives you quite a strong peak. The PureFocus 850 also features motorized offset mechanics for use with biological samples. So we can pick up the reflective plane between the air and the top of the cover slip, or between the sample and the bottom of the cover slip if you're using an oil objective, for example, or a water objective. And then we can adjust the light path of the reflected laser in such a way that your imaging plane is offset from the reflective plane. That was a limitation of our previous autofocus system. Another concern that users might have relating to another dichroic mirror sat in the optical path would be that this is going to affect their life science imaging, their fluorescence imaging. This is not the case with the PureFocus 850. If you are using anything between the excitation wavelength of DAPI and the emission wavelength of something like the Alexa 750, you'll get above 90% transmission of all wavelengths back up to your camera. So you shouldn't have any effects on your imaging there. That being said, the PureFocus 850 is also perfectly capable of dealing with material samples, which are traditionally more reflective. It can even image successfully over uneven reflective planes using what we call our line mode systems. So in our more typical modes, we're taking kind of a point from the center of the sample and analyzing the laser signal from there. In a line mode system, we are taking more of an average signal across the field of view and using that to maintain a more consistent focus over the field of view. Now, I alluded to this earlier. We're talking about this laser signal focused onto the center of your sensor. What we give you with PureFocus 850 is a good view of exactly what this reflected signal looks like. You can determine whether your offset lens is in the right position for your sample by looking at the position of the peak at the center of the sensor. You don't traditionally get this with the split sensor designs that you normally see across the market. What they're more focused on is determining when you're out of focus. With the PureFocus, you do get that, but you also get an indication of when the sample is in focus by virtue of this strong peak at the center of the sensor. You can also use the intensity of this signal to determine if you've got a sample present or not. For example, if you're using an automated loading system, you don't want your autofocus to activate when your sample isn't present. We have triggering mechanisms built into the PureFocus user interface that allow you to deactivate the autofocus mechanism when no sample is in the optical path. We can also use this signal to define the signal used for positioning. So what we might see, for example, is abnormal reflections, maybe from other components to your optical path. Every microscope is different. We can use certain controls to exclude that from the positional recalculation. And also, depending on the intensity of your illumination, we can use another setting to reduce your background. So you're only using useful signal that appears above the background of your illumination. The PR Focus 850 was designed to have a very fast update rate. It updates its position every millisecond. And what this will allow you to do is, rather than when you're doing a TAL scan, for example, moving to a position, refocusing using an autofocus algorithm, and then taking your image, you can be sure that the PR Focus is operating in the background, maintaining focus all the time, so that when you reach your next tile position, you're ready to image straight away. This rapid focus recovery is extremely good with both stepper and piezo systems. In particular with piezo, you can start operating at really fast speeds. I've been working with a sample quite recently where they had a really narrow focal plane that they were interested in. And I was able to use extremely fast settings with the piezo nose piece from Prior to maintain focus on that plane and keep it extremely stable. We also provide controls where you can deactivate the servo mechanism to maintain an enhanced focus stability at a given location. We also give the capability for extended focus recapture, where we can set up protocols to move the sample long distances even when no sample is detected, and then reactivate the servo when we get that sample detection once again. But I've talked about OEM at the start. This product is not set in stone. If from what you've seen, PR Focus looks really interesting, but maybe one of the things I mentioned doesn't quite fit for your system, there are things we can change. We can look at changing the laser wavelength. The 850 nanometer wavelength is designed for use with more conventional fluorescence techniques, whereas if you're using something like multiphoton or perhaps something in infrared, maybe for a materials application, this is something we can look at changing. Similarly, we can change mirrors and lenses to accommodate these types of applications. The offset mechanics used for biologicals, these are motorized and quite dynamic. They can be changed to be more dynamic or less dynamic depending on the application. And finally, we can give you a specific control box to fit within a broader design. So if you're building your own instrument, we can give you a discrete controller that doesn't have to sit on the outside, and you can fully integrate the PR Focus into your system. So the second part of my talk relates to our new nano positioning devices. In 2018, just after I joined Prior, we acquired a company called Queensgate. Queensgate were a spin out from Imperial College London in the 70s, and they literally wrote the book on nano positioning. If you go to our website now, you can download it. And they've been working with us for the past 2 years to develop piezo focusing devices for use in microscopy. This is not Queensgate's traditional area of business, but as you'll see, we're really benefiting from some experts in this field. So I'll start with the new OP400 focusing nose piece. It's a little bit different from maybe some of your conventional focusing nose piece systems for microscopy. It's made from stainless steel, which means it's stiffer and more durable, and that allows us to achieve some higher specifications. It's got a 400 micron range, but it's also got extremely good resolution and repeatability, and more comparable to a 100 micron system. It's got an extremely rapid step settle time. That means that you can move between different slices of a Z stack really fast and be confident that you are going to be exactly where you need to be in your eventual 3D render. It's also got an extremely high load. We saw the Meso lens earlier today. I'm not sure exactly how heavy that is, but this nose piece can support anything up to 1 kilogram. And finally, we've got two parameters at the bottom: high resonant frequency and high closed loop bandwidth. I won't go into too much detail on these two, but what you need to know is that kind of the speed settings that we're able to operate at with this system are dependent on these two parameters. If the resonant frequency is too low, you're more prone to resonance within your system, meaning that you'll have difficulties relating to focus instability. And also this high closed loop bandwidth parameter, this means you can input more commands within a time frame to ensure that your focus correction is absolutely optimal. We also have stage systems now. We used to do a nanoscan system previously, but we wanted to bring the manufacture of these systems in-house to have more control over their performance. So we've now got a range of these products ranging from 200 to 600 micron range with similar sort of performance capabilities, the OP400. Similarly, you get extremely rapid Z scanning, and again, you get the capability to have really rapid settle times over long distances. So that 20 millisecond settle time is over 100 microns. So you can imagine you've completed your first Z stack in a time series and you want to go back to the first position. You can do that with this, with the SP range systems without having to throw away some images at the start of your next Z stack. This settle time also benefits autofocus applications, like I was mentioning when I was talking about the PureFocus 850. Behind all of these parameters is Queensgate's electronics. You can program in things like motion control and velocity control, which gives you the smooth ramping, which again was assisting me with my autofocus application, and also enables the settle time specification. It can also give you the capability to do constant velocity scanning. So instead of taking point-to-point images up through Z, you could trigger an image at a given location within Z without ever stopping the motion of your sample. The speed specifications that I've given you, part of the way we achieve such speeds is we remove some of those resonant frequencies, which, if you remember, give you that focus instability using notch filters. And we also use a feed-forward algorithm to predict where the system is going to be ahead of time, so we can more quickly correct any positional errors along the way. These systems are compatible with Micromanager and Metamorph, and some other third-party compatibilities on the way. Queensgate's more traditional business has been in the OEM market, and they actually assist in the production of over half of the world's hard disks through collaboration with Seagate. Article was recently published in Physics World. And the development of this system was brought about by some quite difficult requirements, where the positional error budget for Seagate's quality department was about 500 picometers. They couldn't deal with a system that would be less accurate than that. And through the persistence and expertise of our engineers, we were able to bring this down as low as a 93 picometer resolution. To compare that to the system we were just talking about, that is an order of magnitude better. In addition to that, we were looking for that extremely high focus stability, that large resonant frequency, and following on from there, we had some really excellent feedback from Seagate, and we're very proud of that. Secondly, Queensgate also have an excellent relationship with the National Physical Laboratory, NPL. They supply XY stages for multiple AFM systems. But more recently, NPL were working on realizing the meter at atomic scale. If you remember, we went through a phase where we were recalibrating a lot of our SI units. One of the less well reported on one of those was the meter. And to do this, NPL required a system that had quite a long travel range, about 450 microns, but operating at 10 to 20 picometer resolution. So again, an order of magnitude better than what we were what I've just shown you with our new microscopy products, and also supporting extremely high workload. Queensgate worked collaboratively with NPL to design the system and gave them an out-of-the-box solution that worked exactly as they were expecting it to. Finally, I've alluded to OEM throughout this entire presentation, and we are very keen to expand our horizons beyond components of microscopes and start delivering bespoke microscopy solutions for niche applications. And the way we're doing this is by providing a framework for system design. OEM is not new for Prior. We've had success in this area over recent years as well. We operate in approximately 2 modes. We can design OEMs from component-led ethos, where we take one of our existing products and we build a system around it. What you're seeing on the top line there is a tool for analyzing a specific cell type. That kind of led on from the customer needing a fast, robust motorized XY stage. And also we can do complete black box novel design, where we can take customer requirements without any hardware and design the system to meet those. Both of the systems you see on the right hand side of the slide, we are selling tens of or more throughout the year. But how can we facilitate more business in this area? How can we provide more interesting and more niche solutions, or help to provide them rather, through the use of our automation expertise? We've now got 2 rapid development platforms under the OpenStand product name. We've got an upright and an inverted system, which can be built up with our existing products and have all their optics design in place. So kind of that aspect of a product design wouldn't necessarily need to be considered in great detail out of the box. You can build off this system and define exactly how you want your imaging protocol to work. You can use our existing product range, or you can take something from our product range and ask it to be modified. So this drawing we've got in the middle here is of our 8-slide stage, which has been converted to a 4-slide stage with a 4-slide preview station. So you can image a preview of your 4 slides before moving on and imaging those 4 slides again at higher magnifications. And finally, we have also been designing completely new XY systems, such as this micro manipulator. We're working with applications from across the microscopy field. We're looking at high throughput systems that use our experience with robotic loading. We're looking at parallel imaging of fixed slides, so imaging a slide at low mag whilst imaging an adjacent slide at high magnification. We're working with customers ranging from billion-dollar revenue engineering firms through to university spinouts. And we're also using our high precision technology to assist with applications such as high precision material deposition. To kind of assist with this slight change of tack in the kind of business that we're doing, we've expanded our product management team threefold in the past 2 years. And if you have any inquiries about our OEM capabilities, please go to our website and contact your regional Prior team. Thank you very much for listening, and I'll stop talking now because I think I'm being ushered off the stage. If we have any questions.
I was trying to work out, like in a normal conference, I'd just stand up, but it was a bit hard. Yeah, and just in the interest of time, thank you very much for that. That was really good. And you know, we're happy to work with you guys. We use your stages a lot in demos. We have one in our own lab. So really nice to hear about more of your OEM solutions. There were just a couple of questions that came in towards the start of your talk, the original stage. So Britta was asking, how large can that offset be?
Because the Pure Focus is designed to work with almost any system by sitting into that infinity space, that figure is quite hard to define, but typically we're using conventional slides of about 0.15 thickness. However, it depends so much on things like magnification. We could definitely go greater than that. If she wants to talk to us afterwards about her application, I'm sure we could give her a clearer answer depending on her system.
Sure. And just a quick last question from Rito. For the watery cell samples, does the max opening angle of the objective matter for your autofocus system?
So presumably that would be in relation to the NA.
Yeah.
So we, in a sense, it does matter, but we've tried out this system with a high number of with a large number of objectives, and we only really start to see problems with low magnification at high NA objectives.
Okay, yeah, understood. Okay, thank you very, very much, Simon, again for rearranging everything and staying so late. Really appreciate it. So let's move on. So we'd like Daniel to join the room. So just while Daniel's getting online, this is Daniel Fulton. So Daniel completed his PhD in neuroscience in 2003, where he focused on cellular mechanisms of learning and memory. He then worked in the USA for a while and returned to the UK to Warwick University. He moved to Birmingham to take up a fellowship in 2013. He now leads the oligodendrocyte and myelin research group there. So he's going to talk to us about long-term live imaging, oligodendrocyte myelination in organotypical brain slice cultures. That's a bit of a mouthful, Daniel. I hope you do a better job than I will. Over to you.
It's quite understandable. It's been a long and hard couple of days for Philippa.
Sure.
Yeah, so I just want to thank Philippa and Lee and the team at Aurochs for organising this excellent microscopy conference that I think we're all enjoying a great deal. So I'm very pleased to talk about my imaging results that we have and the methods we've developed for analysing oligodendrocytes and myelination and achieving long-term live imaging of these events. So briefly, just to go through the contents of what I will present to you, I'll give you a little background on oligodendrocytes and their role in myelination in the CNS and how this is crucial for both the health and the response to disease in the brain. I'll then give you some examples from other groups who have been achieving live imaging of myelination, in particular looking at some results from zebrafish and from in vivo imaging in the mouse. And then I'll introduce the system that we use in my group, which is the organotypic slice cultures taken from the forebrain, and which we're now using to try to get long-term imaging of myelination in deep subcortical white matter. I'll introduce the imaging system we have and the protocol that we recently developed. And I'll end with some very preliminary results from this system. Oligodendrocytes are the glial cells in the CNS which perform myelination. So myelin is a spiral wrap of the oligodendrocytes membrane, which is formed during CNS development. The processes of the oligodendrocytes make contact with an axon and then begin to wrap around that axon. And they synthesize lipids and specialized proteins which are compacted down to form this nice insulating material. Myelination enhances conduction velocities, improves the fidelity of transmission of signals, and more recently has been understood to, through the addition and modulation of myelination, lead to possible changes in circuit function. Myelin has other roles as well, for example, providing metabolic and trophic support to the axons. So myelin is generally essential for neurologic function, and understanding the mechanisms that control myelination could provide novel ways in which to study therapies for promoting the repair of myelin in CNS diseases where myelin is degenerated or attacked. I'm just going to skip through these two slides here in the interests of time and bring you to these slides here where we'll look at the types of work that has been done previously to image myelination in vivo. So on the left, you can see some data from larval zebrafish. Now, larval zebrafish are excellent for this type of work because of their transparent bodies, which allows imaging of fluorescently labeled cells in situ. You can see these are images taken from a transgenic zebrafish larva where a membrane tag GFP is being driven, the expression of which is being driven by oligodendrocyte lineage promoters. Now, in this study, it was possible for the researchers to see how those oligodendrocytes are beginning to form nascent myelin sheaths, which have been highlighted in cyan there. And of particular note, they noticed that oligodendrocytes produce all of the early myelinating sheaths that those cells would produce in their lifetime in just 5 hours. A very short window of time, considering that the segments that they produce, those myelinating segments, will last for many months. On the right, we can see results from mammalian systems. So this is taken from studies of mice where they've done in vivo imaging using the cranial window method and the 2-photon microscope. So the technology here is able to resolve fluorescently labeled oligodendrocytes down into the middle layers of the cortex. And here you can see on the right some images of oligodendrocytes that have been imaged in this way. And this is really a classic mature myelinating oligodendrocytes. You can see these nice parallel aligned GFP labeled profiles. These are the myelin segments produced by that individual oligodendrocyte. So this type of in vivo imaging can be performed in adult mice, and it enables researchers to study the behavior of these cells in the mature CNS. But there are some limitations to this approach. It's hard to implement it in developing CNS in the smaller animals. And so some knowledge on how the early events of myelination are occurring, the dynamics of those events, haven't really been resolved yet. In addition, you can see from the diagram that the 2-photon imaging beam is not able to reach down into the deeper layers of the cortex. So areas, in particular subcortical white matter, which are really key areas for understanding myelination. These are the pathways where you have many axons that become myelinated. They can't be imaged using this current approach in vivo. So to address some of these problems and to begin to do live imaging over the long term of subcortical white matter, we've begun to use organotypic brain slices. So here we can see some examples taken from 4 brain slice cultures that we produced in the lab. So the slices are vibrotome cut to about 350 microns, and you can see a little diagram there to show you the architecture of the slice and the areas that we're interested in. So the subcortical white matter is illustrated there, and in these immunostaining images taken from the slice cultures, we can see 2 regions. We have the subcortical white matter at the bottom and the cortex at the top, and delineated by these dashed lines. Now, this is immunofluorescent staining for MBP, which is one of the key myelin proteins. And here we can see that around 2 days after making the slice cultures, we have a nice population of oligodendrocytes in both the cortex and the subcortical white matter, but they haven't begun to elaborate their myelin segments. You can't see any straight parallel profiles there. Now, if we wait 5 days in culture, we see that those oligodendrocytes begin to initiate their myelination. And we see nice processes appearing there in both the subcortical white matter, quite a density, and also spreading out up into the overlying areas of cortex. So using this system, we're able to track and observe the appearance of myelination. Now, this, of course, is in fixed samples that have been stained for various proteins. But, of course, what we really want to do is do some live imaging and try to capture the dynamics of these events in these deep-lying areas. So in order to do that, we're using this particular imaging system. So this is our spinning disk. This is the DSD-1. So I think we saw some of Philippa's slides earlier. This sits on the timeline of the Aurochs technologies in around 2011. So it's one of the older systems. And this is a technology that was actually packaged and sold by Andor Technologies. So we have an inverted Zeiss Axiovert, a metal halide lamp, and then on the right you can see the DSD module, and is attached to an Andor Clara CCD camera. So in order to actually image the oligodendrocytes and their behaviors in the living slices, we use a reporter mouse. And this is the PLP, which is a promoter for mature oligodendrocyte protein, proteolipid protein, and that's driving the expression of DS-red fluorescent proteins. Now, we can see an example of a confocal picture taken with the DSD. This is actually a volume rendering that we've done using a mirror. And I think if we just try this movie here, we should be able to observe. Let's see if this works. I don't know if you can see that, but this is a kind of a flyby of the cell. And you can see that this oligodendrocyte is producing a number of parallel aligned processes, which we take to be either developing or maturing myelin segments. So we can see that the DSD is able to give us a nice resolution of this oligodendrocyte. Now, again, this is in a fixed section. So what we really want to be doing is looking at the capabilities to do live imaging. But there are some challenges to doing live imaging of organotypic slice cultures. The main issue is, of course, these events are over the long term. We need to be able to stabilize this tissue and image the cells on the order of hours to days, because myelination is a slow process. And the slice cultures themselves are actually growing at an air-medium interface. So they're cultured on top of a membrane insert. You can see this in the diagram on the left. This is like a little table inside the imaging dish. And the slice is on top of that with a nice nutrient-rich medium underneath. Now, the key challenge is the distance between the sample and the objective, because the insert and the chamber in which this is placed is going to lift it up quite high above the objective. So it's important to use a long distance objective, and we're using a 10x 0.25 NA here. The second requirement, of course, is an incubator on the microscope, and we're using this miniature environmental chamber, which provides a very compact device for maintaining the slices. So this chamber is actually able to keep the slices in the same conditions that we would have normally in the incubator. And with this setup, we're still able to image these cells quite nicely. So you can see an example on the right here of some DS-red oligodendrocytes. You can see very nicely labeled cell bodies, but also you can see those fine DS-red labeled profiles running in parallel to the cell bodies, which are the developing or maturing myelin sheaths. So in order to start to do some live image studies of these oligodendrocytes, we came up with this initial protocol where basically the slices were shuttled between the incubator and the microscope on a daily cycle, taking some pictures once every 24 hours. Now, this had the disadvantage that it's necessary to relocate the cells within the sample each time. This is possible, but very time-consuming. But even so, we were able to find some interesting initial results right away. You can see that within around 24 hours, these oligodendrocytes are already setting up and producing most of the sites that will go on to be elaborated into putative myelin segments. So interestingly, these sites are already there after 24 hours. And what follows in the next few days is simply an elaboration and an intensification of those structures. So it seems that there are many interesting things happening very early on within that first 24 hours. In order to study those events, we realized that we needed to maintain the slices in the micro incubator on the microscope for prolonged periods of time. And after experimenting with a few different conditions, we were able to get a nice stable environment for the slices and keep them on there for up to 31 hours. So with the slices maintained in that situation, we developed this protocol where essentially the slice was imaged with a Z-stack every 1 hour. And again, using the same objective, you can see some examples of that on the right. So here you can see we're actually imaging here the subcortical white matter of the slice. And that's shown as a little region of interest on on that little diagram above, we can see an example of one of these time-lapse experiments here, I think.
Play now.
Yeah, so now you can see that initially at the start of the movie, there are very few of these profiles, but they appear gradually over time. And by 31 hours, the number of processes has kind of reached a plateau.
Just run that again for you.
Great. So some observations from that movie is that, first of all, the cells are remarkably stable over that prolonged imaging period. So we don't see any signs of damage due to the prolonged exposure either to the imaging conditions or the conditions on the microscope. Also, the 10x objective, whilst having quite a low NA, is quite good at capturing the resolution, resolving the dynamics of those processes being generated and extended. We also noticed that some of the processes are retracted over time. They seem to disappear in the imaging frame, whilst others remain very stable. Seems like a few, it's a minority that are retracted, so the majority are quite persistent and stable over time. Of course, we wish to quantify these images and get some data out of them. And so to do that, we've been using ImageJ and a plugin that's available called Simple Neurite Tracer. And with this software, we're able to, working with the image stacks at the different time points, trace out paths that represent the processes being generated by these oligodendrocytes. So you pick a start point on a process as it appears, and then an endpoint somewhere along that process, and then the computer uses an algorithm to trace through the image stack in order to pick up the potential processes. And you can see that on the right, if we go through the time points, this is just a few that we selected, you can see that the number of these paths increases over time until we reach the end of the experiment at 31 hours on the left. So we're able to quantify a number of parameters here. I'm going to show you some quantification of the total number of paths and the total path length for the whole of the image. You can, of course, also look at single cells. So just to give you an idea, can we play another video now, Lee? I wonder if you can start the traced paths movie.
Trace path. Okay, got it. 2 seconds.
So this should give us a little flyby through the image that's been traced out with the plugin, and you can see some of the processes in red, and the ones in blue are processes that belong to an individual cell that we've traced out. So we can look at both single cells or the whole image. Those are some movies that we created using Amira.
You might want to just play it again. It says something about muting while it plays to give it the bandwidth, I guess.
Okay, so you can see that we've got tracings of the processes belonging to the cells, and so they're quantified. So Neurite Tracer will give you the length of those, and you can also, of course, get information about the number of those in the image. And when we took that preliminary data and we've analysed it, what we find is that over the time course of these experiments, both the total path number for the cells and their path length seem to reach some form of plateau within that imaging time frame. So within around 25 hours, the development of these processes appears to come to a flat sort of maximum, which is an interesting observation. I obviously point out this is preliminary work and it definitely calls for further validation, but it seems that at least initially in this system, in the subcortical white matter in these slice cultures, the period of time in which these oligodendrocytes are elaborating their processes, developing their initial myelinating segments, seems to all occur within around 25 hours. If we look at the individual cell analysis, here you can see on the left we've picked out 3 cells, and 2 of those cells, cell 1 and cell 2, this is looking at the number of paths on the cell. We can see that they both reach a a maximum around 11 and 14 hours, and the third cell may or may not have reached its peak. So again, showing that somewhere between 10 to possibly 20 hours, these cells are completing the establishment of their initial points at which myelination will begin. They may then go on to elaborate these processes, of course, but the number of actual new processes seems to be halted at that point. So just to conclude here, the early myelination events can be imaged in these forebrain slice cultures, and the setup that we've developed seems to be a very stable environment for these prolonged studies. It seems that we can quantify the maturation of these oligodendrocytes and their processes quite easily from the confocal time-lapse images that we're collecting. And at least in the subcortical white matter of these slices, the oligodendrocytes seem to have quite an extended window of maturation when compared to that observed in lower vertebrates like the zebrafish larva that we looked at in those initial background slides. So we're quite interested to develop this method, and it might have some very interesting applications perhaps as a screening tool for analysing the effect of pro-myelinating compounds. It might be quite a useful way of looking at the effects of compounds that might promote myelination and seeing how it affects the early events and the kinetics of that. So finally, I just want to end by highlighting a workshop that we're going to run at Birmingham. So we're using a number of different slice culture and explant models at the university. And so this workshop is set up to teach the methodologies for producing these slice culture and explant models and demonstrate their use with a number of different experiments. So we're going to be demonstrating the mouse slice cultures that I've shown in my presentation today, but also some human cartilage explants, human lung slice, and human liver explants, and with a range of various methodologies. So if you're interested in learning about these slice culture and explant methods, then please take a look at our link there. You can find more information and you can register for the event, which is planned for Wednesday, the 25th of November. Okay, well, I'll stop there and happy to take some questions.
Thank you so much for that, Daniel. That was a really interesting talk. Thanks, some great biology there. And I'm really pleased to see a DSD1 still working so well and creating some good images. So it just shows that if you look after a piece of equipment, then it will go on for a very, very long time, especially if it's manufactured by such a good company. One comment: do you want to have a Unity microscope at your workshop to play with some samples?
We do indeed. That would be an excellent addition.
Yeah, be great to see how it compares to the old version, the DSD1. Okay, you had a couple of questions come in while you were talking. So one was from Hilary. How are you dealing with the autofluorescence inherent of the brain in these samples?
We don't seem to find that to be much of a problem with our particular imaging session, with our imaging protocol. So with the data I've shown you today, that is using one particular filter set that comes with the DSD. And so, of course, we're imaging, I think it's on the slides back there, but exciting around 560 and collecting at around 610 nanometers. And under those conditions, we really don't see any issues with autofluorescence. In addition, the DS red signals are very bright, so it's very easy to collect those and set up in a way so that we don't have any issues with background.
Cool. So it's really your filter set choice is key in this case. From Lydia and also Gaurav, they were asking about your insert. How do you make sure the focus is maintained over time, as these slices tend to float a little? They'd both like to know more about your sample insert.
Okay, so first of all, the inserts, we're using the Millipore inserts, and these are I believe they're the 0.4 micron pores, and they are, I can supply the catalog number if anyone's interested in that. They're just the standard membrane inserts that are used for 6 well plates for slice cultures.
Okay, cool. So maybe people can contact you directly to find out a little bit more about your protocol if they want to.
So the question about the slices floating. So that's not an issue in this situation because the way we prepare these slice cultures is that they're placed on top of the membrane insert, and then they're really at this interface with the liquid, literally just at the right level so that it's able to keep the slice moist, but the slice is not, there's no movement at all, it's stuck down. And as they grow after a few days, they really knit down onto the membrane of the insert.
Okay, that's cool. And how thick are these samples?
Well, at the beginning, when we make the vibratome sections, they're 350 microns, which is quite thick. But over time, if you have a healthy, viable piece of tissue, it will begin to thin down, and it could go down to anywhere around 150 to 200 microns.
Okay, and how deep are you managing to image into that tissue with the DSD?
Yeah, I would say that once they're thinned out like that, we're probably imaging down to around 50 microns, maybe 40.
Okay, so fairly deep in. Okay, cool. So there's a question, have you tried to look at the myelination using a point scanner confocal in reflection mode? They tend to reflect different colours differently due to the interference on the multi-layer structure.
So when I was a research fellow at Warwick, I was using a point scanner. I was using a SP5. So at that point, that was a number of years ago, we did try to use that for imaging myelination, but it was an upright microscope and it was not very suitable for the slice cultures for long-term imaging. So it wasn't particularly successful.
Okay. So on an invert, it might work better, but you haven't tried it.
Much better with an invert because you haven't got that problem of trying to image above the slice whilst keeping it in the interface configuration and keeping the atmosphere and temperature and humidity correct.
Mm-hmm. And a question from Lydia. She's saying, since you image through the filter, do you have less oxygenation at the bottom of the slice?
So I don't believe that's a problem because the slice, again, it's not submerged. So it's sitting atop this insert and then has good access to the atmosphere inside the chamber.
Okay, and maybe a final question, unless any more pop in, from Alessia. What do you think about the use of light sheet fluorescence microscopy or one of the previously seen mesoscopic techniques like the mesolens? I guess compared with the DSD1. Discuss.
Well, I can't comment on the mesoscopic techniques. I would say that if we were comparing these technologies, I'd definitely go back to what Philippa has said already in her presentation, which is that the DSD is extremely cost effective. I was setting up my group a number of years ago, and with the funding I had at that point, it was possible for me to buy an entire system. I had the microscope already, but to get the camera, the spinning disc unit, and the light source and the software all in a package that was really quite affordable. And having run it for a number of years, I can also attest to the fact that the maintenance costs are very low. I'm using metal halide bulbs. They're costly, but you don't need to replace them very often. So from a practical point of view, and saying if you wanted to set up a lab to do this type of work, and you weren't part of a core facility, then I'd say this type of imaging setup is really ideal.
Cool, thank you. You should become a salesperson for Aurochs. But obviously, yeah, I mean, if you have access to a light sheet or something like that, then it's going to be brilliant. But as you say, for your own research in your own lab, then maybe one of these more affordable and compact instruments might be good. Okay, so unless there are any more questions for Daniel, I will let him go and enjoy his evening. Again, thank you for staying so late, Daniel, and rearranging your day to speak. It was a really great talk, and yeah, I think they will appreciate it.